All right, let's get into it. Today, we're going to be chemical detectives. We're diving into a mystery, cracking the case of a substance that you probably see and eat every single day. Its true identity? Well, it's hiding in plain sight.
I mean, this stuff is everywhere, right? It's what makes bread, rice, and potatoes so hearty and energy-packed. We're talking about starch, of course. Seems pretty simple on the surface, but trust me, this everyday compound is hiding a pretty big secret.
And that's the big question, isn't it? That's what our investigation is all about. We see it, we cook with it, we eat it, but what is it really on a molecular level? To figure that out, well, we're going to need to gather some clues and run a few tests.
So every good detective story kicks off by building a profile on the main suspect. So that's what we're going to do. We're running a series of chemical tests to figure out starch's basic identity before we even try to break it.
First up is something called malicious test. You can think of this as a really general background check. Is our suspect even part of the right family of compounds? This test gives us a straight-up yes or no answer to a simple question. Is starch a carbohydrate? And there it is, our first clue. We mix the starch with Amylase's reagents, and look at that, a really distinct reddish-violet ring forms. That's a positive ID. It's official. Starch is a carbohydrate. We can add that to the case file.
Okay, so we know it's a carbohydrate, but now we got to get more specific. Is it a simple little sugar, or is it something bigger, much bigger? That's where the iodine test comes in. It's specifically looking for polysaccharides. We're talking the absolute heavyweights of the carbohydrate world.
And would you look at that? A couple drops of iodine and boom, our solution turns this intense deep blue color. This is the classic telltale sign of a polysaccharide. So our suspect isn't just any old carbohydrate, it's a huge, complex one. Okay, now things are getting interesting. All right, one last test for our initial profile, Benedict's test. This one checks for something we call reducing sugars. Now, to put it simply, this test tells us if our carbohydrate is a simple reactive kind of sugar. If it is, the test will change color. If it's not, well, nothing will happen.
And the results are in. We add our starch to the Benedict solution, we heat it up, and the solution stays blue. No change at all. This tells us starch is a non-reducing sugar, so our initial profile is complete. Starch is a big, complex, and pretty unreactive polysaccharide.
Okay, now that we have a good profile on our suspect, it's time for the interrogation. We're going to apply some serious chemical pressure to force this starch molecule to tell us its secrets, to reveal what it's really made of.
So, our interrogation technique is called acid hydrolysis, and it's actually pretty simple, but really powerful. You take a starch solution, add a strong acid, in this case hydrochloric acid, and then you heat it all up in a boiling water bath. That combo of acid and heat, it acts like a chemical sledgehammer, just smashing that giant starch molecule into pieces. Now this is where our detective story gets really visual. We're going to bring back our old friend, the iodine test. But this time, we're not just using it for a one-time ID. We're going to use it to watch the breakdown minute by minute. We get to see the starch molecule literally fall apart. Check out this timeline. After 1 minute, we still see that intense blue color of starch. But by 5 minutes in, it's shifting to purple. That means the starch is breaking down into smaller pieces called amylodextrins. At 10 minutes, it's red. We're getting even smaller pieces called erythrodextrins. And then, finally, after an hour, the solution is totally clear. The polysaccharide is gone. So, the breakdown is complete. Our big, complex suspect has been totally broken down into its most basic parts. The interrogation worked. But what did we find? What's left over? It's time to identify the final product. Hey, remember the Benedict's test from the beginning? When we tested starch, the solution just stayed blue, telling us it was non-reducing. Well, look now. After we broke it down, we run the same exact test and bam! A bright brick red color. This right here is the smoking gun. It proves that our big, non-reducing polysaccharide was broken down into simple, reducing sugars. This is a huge breakthrough. We know what starch is made of. It's built from simple reducing sugars. But you know, there are lots of different kinds of sugars out there. We need to make one last final ID to officially close this case.
So for our final piece of evidence, we're pulling out Seeley-Wanoff's test. This is a very specific tool. It's designed to tell the difference between two major types of simple sugars, aldose sugars like glucose and keto sugars like fructose. If we had a keto sugar, the solution would turn a distinct cherry red.
So we run the test on our final solution, and absolutely nothing. No color change at all. And this negative result is actually our final confirmation. Since we didn't get that cherry red color, we know the building block isn't a keto sugar, it has to be an aldose sugar, and specifically, it's glucose.
And there we have it. The secret identity has been revealed. The mystery is solved. So let's just close out the case file by reviewing all the evidence one last time.
The case file tells a really clear story, right? We started with our suspect, a big, non-reducing polysaccharide. Our interrogation method was acid and heat. We watched it transform, breaking down into smaller and smaller dextrins, and in the end, we unmasked its true identity. It's made entirely of a simple reducing sugar, which we confirmed is glucose, an aldose sugar. So, the final verdict is crystal clear. After all the tests, all the evidence, we can say for sure that when you break starch all the way down to its most basic component, what you're left with is glucose. Case closed.
But hang on, here's one final thought to leave you with. We needed boiling water and concentrated acid to do all this in an hour. Your body performs this exact same chemical reaction every single time you eat potatoes or bread. But it does it at body temperature with no harsh acids. So how does it do that? The secret is enzymes. But that's a detective story for another day. Thanks for joining the investigation.